Welcome to the Merlin Metro News Network. Today's program continues our two-part series on the generator circuit. Now that the basics of the system and its components have been covered, we're going to take a look at how these components work in detail. We'll also show how these components interact to produce and regulate electrical power on board the aircraft. If you had any questions or confusion regarding what has been covered in the DC power and distribution tapes, we hope you have done some supplemental study or asked someone for some individual help. While the generator system is not in itself really more difficult or theoretical than the feeder fault system, it is more complex. Now let's begin our first program.
We've learned some of the general features of the aircraft generator system. Now let's discuss the operational details. In order to reduce the complexity and fear that usually accompanies larger multifunction circuits, we'll describe and explain each of the major component functions separately. Afterwards, we'll put them all together, and many of the interactions between them will become clear. Since the regulator is the brains of the generator circuit, once you understand it, the rest of the circuit is simple. Let's begin with the starter generator. This component has already been described in a previous tape. Now let's look at its internal workings in a little more detail. We will begin with what the starter generator begins with, residual magnetism. Residual magnetism is a characteristic of all electromagnets. You've probably seen someone magnetize a screwdriver by making it into an electromagnet for a short time. Inside of a generator, the field coils use electromagnetism to produce the lines of flux which are cut by the armature coils. When the electric current being supplied to these field coils is removed, most of the magnetism disappears as well. But a small amount, referred to as residual magnetism, remains. It is this small amount of magnetism that will allow the generator to begin producing electricity as soon as it begins turning. If we were talking about a pump, we would refer to this as its ability to prime itself. Without external control and regulation, the voltage being produced under this condition is very small, but is enough to get things started. If for some reason the residual magnetism is lost or is too weak to begin the generating process, it must be externally assisted. This is done by passing a current through the field, or flashing the field as it is commonly called. Because of the materials used in aircraft generators, they retain their residual magnetism for long periods and do not normally need to be flashed. As we will discuss later, a circuit within the generator system flashes the field during reset operations as well. Another point we must consider is the construction of the generator itself. Up to this point, we have talked about the field windings only. There are other coils and groups of windings within the generator as well. The interpole windings are in series with the armature and ground. Any current that flows through the armature flows through these windings as well. A connection is made at the junction between the armature and interpole windings, which we refer to as the generator D-lead. Because of its location in the generator circuit, the D-lead can be used to sense valuable information about the output of the generator. It is one of the primary sensing points used by the control panel in determining whether or not the generator is functioning properly. As we explain the inner workings of the control panel, the significance of this connection will become evident. Let's review the other connections as well. The A-lead connection is the entry point for current to flow into the field windings. This current will create electromagnetism in the field, which in turn will allow the generator to create electricity. Even though the current flowing into the A-lead is much smaller than the current being produced by the generator, they are in fact directly proportional. If we increase the A-lead current flow, the generator output will increase. If we decrease the A-lead current flow, the current will decrease. Returning to our pump analogy, we can think of the A-lead as a governor connection, a smaller force that is able to regulate the output of a larger force. The B terminal is the output junction of the generator. The power being delivered by the generator for use on board the aircraft is delivered here. The B lead terminal is also a connection point for the control panel for sensing and monitoring the voltage output of the generator circuit. The C terminal is where power is connected for using the starter portion of the starter generator. This connection leads to a separate set of windings that are used to make the generator into a motor to drive the engine during start. This circuit is of relative unimportance to the generator circuit, although, as we will explain later, the starter windings within the generator do play a part in the generator circuit as well. The D lead, which we've already mentioned, is the last connection. It is purely a sensing point to be used by the control panel in determining proper operation of the generator system. Now let's discuss the regulator, or generator control unit, in more detail. This compact unit provides most of the control and regulating functions for the generator circuit. It's difficult to discuss the control panel's inner workings without discussing the external circuitry likewise. It is also somewhat difficult to understand the external circuitry without some understanding of the internal workings of the control panel. We'll therefore be going back and forth between internal description and external description as necessary to adequately explain both. We'll start with the external circuitry. We'll use this simplified schematic in which we have omitted all plugs, terminal strips, and duplicate wires. Note that several relays are installed in the circuit. They are the generator on relay, the output control relay, and the main contactor relay, or generator relay as it is often called. Also included in the circuit are several circuit breakers that protect various parts of the circuit. The generator on/off reset switch located in the cockpit switch panel. A variable resistor that allows us to adjust the output voltage of the generator, and two limiting resistors. The generator on and reset relays are controlled by the generator switch in the cockpit. This is a 3-position switch, with a reset position spring-loaded back to the center off position. Due to this arrangement, the reset relay will only be engaged while the generator switch is held in the reset position, while the generator on relay will be closed anytime the switch is in the on position. The output control relay is energized during the engine start cycle from 0 to 55%. When energized, it disconnects the power into the control panel supplied from the B lead of the generator and the power to the field that will be provided through the generator A lead. Points worth noting about the circuit at this level include the status of the generator main contactor, whether open or closed, is dependent upon the control panel and position of the generator switch in the cockpit. Regardless of pilot action, the main contactor will not close and place the generator online unless the control panel so commands. The control panel uses several points throughout the system as sensing points to determine if proper operation is occurring. The points include the E, B, A, and D leads of the generator and the voltage present on the bus. Not shown in this illustration, but of equal importance, are the generator wiring fault transformer inputs. If the control panel senses an abnormality at any of these points, it will prevent the generator from coming on the line or from remaining on the line by immediately opening the main contactor relay. Although the control panel has control of the main contactor relay, the pilot, through the switch in the cockpit, still has the ability to immediately disconnect the generator by moving the switch to the off position. The output control relay is energized during the engine start cycle between 0 and 55 to 60% RPM. Even though the starter generator is used as both a motor and a generator, it can never be used for both functions simultaneously. Significant damage to the starter generator and aircraft wiring could occur. To absolutely ensure that this condition never occurs, the output relay disconnects the field excitation circuit connected to the A terminal of the generator and disconnects the control panel connection of the generator B terminal as well. With the B connection broken, the power needed to operate the electronics inside the control panel has been removed, making the entire generator inactive. It is the power provided through the B lead that makes the generator system a self-excited, self-powered system. An additional important reason for disconnecting the A lead and B lead circuits during engine start is to prevent damaging voltages from entering the internal circuitry of the control panel. The reset relay is energized only when the generator switch is held in the reset position. Two sets of contacts within the relay play a dual role. The main function is to provide a path of residual and subsequent increasing voltage from the generator B terminal through the output control relay, into the control panel, back out through the reset relay, then back into the panel. This seemingly long, drawn-out loop serves two important functions. The increasing voltage is flowing through the field coils, which increases or flashes the level of magnetism being produced by the field. This increased magnetism level will in turn increase the generator's output. Simultaneously, the increasing voltage buildup will soon reach a level that will unlatch a trip relay within the control panel. The closing of the contacts of the trip relay is the first step in the control panel beginning to regulate the generator's output. The second set of contacts in the reset relay provide aircraft bus voltage to hold the panel's reset coil engaged and to provide a small trickle voltage via a 400 ohms resistor into the field circuit, thereby providing a secondary flashing of the field. The generator on relay also has a dual role. When the generator switch is turned on, the relay engages, closing two sets of contacts. The first set connects a sample of the bus voltage through a circuit breaker to the reverse current and auto line contactor amplifiers inside the control panel. The second set of contacts allows the output of the generator B terminal to be routed into the control panel. Before we begin our detailed discussion of the internal workings of the generator control panel, let's consider its operation from a function standpoint. The control panel performs two major functions in the generator circuit: controlling the current supplied to the field and controlling the closure of the main contactor relay. The main contactor relay coil receives power from an auto line contactor amplifier circuit within the control panel. The contactor amplifier receives its input from a comparator amplifier. When the comparator amplifier has an output, the auto line contact amplifier will have an output, and thus the relay will close. For the comparator amplifier to have an output, it must sense that the bus voltage, generator voltage, and voltage present within the interpole windings in the generator are at their proper levels and polarities. When each of these signals is correct, the comparator amplifier will have an output, which will cause the auto line contactor control to close the main contactor relay. Fail circuits are included in the control panel that receives input from several external sensing circuits. If a failure is sensed, the trip relay circuit will become active and disconnect the field of the generator by opening the trip relay also installed within the control panel. The combined efforts of these two circuits, the auto line contactor control and the trip relay control, prevent the generator from coming online or remaining online if a fault condition occurs. After protecting the generator and aircraft circuits, the second primary responsibility of the generator control panel is to regulate the output of the generator itself. This is accomplished by two circuits within the control panel. The first is a voltage comparator that compares the output of the generator with a master reference voltage. When the generator output is less than the reference voltage, the comparator will have an output that will eventually cause the generator output voltage to increase. If the generator output is above the reference voltage, the comparator will have no output, which will eventually cause the generator output voltage to decrease. The reference voltage is generated within the control panel and is adjusted during the generator paralleling process. We said that the voltage comparator would eventually affect the generator's output voltage. This is because the output of the voltage comparator must go through another stage, called the voltage regulator. The input to this stage is the output of the voltage comparator and the paralleling circuit, which is an electrical link between the two control panels. The voltage regulator will compare the outputs of the paralleling circuit and the voltage comparator circuit and determine whether the generator field current should be adjusted up or down. The voltage regulator circuit will attempt to maintain its generator's output within the proper output voltage requirements, and yet still maintain an equal load sharing with the opposite generator.
Well, after this big build-up, we're finally going to discuss the internal workings of the generator control panel. Some of you may not absolutely understand everything presented in the next section. This is not as bad as it may sound, since you would never disassemble or attempt to repair the control panel yourself anyway. What is important is that you understand the internal workings of this unit well enough to be able to troubleshoot the external circuitry of the generator system. With that in mind, let's begin our discussion of the generator control panel.
Now let's look at some of the internal details of the control panel circuitry. Here is the auto line contactor circuit. The action starts here with a device called an operational amplifier. Inputs to this device are provided by the B and D leads of the generator. The control panel uses this flow as one of the factors to determine that the output of the generator is not reversed. When the generator switch is moved to the on position, the generator on relay closes. Power now travels from the B lead, through the control panel, through the closed contacts of the on relay, and back into the regulator panel. This power is also routed to the first operational amplifier, which now compares the generator voltage and the bus voltage. If all these voltage levels are correct, an output will be provided. This output will also cause a second operational amplifier and several transistors to begin to operate. This entire group may be thought of as a large amplifier circuit. The output of this circuit will provide the power to close the main contactor relay and to close a relay within the control panel that is part of the generator paralleling circuit. Also included in this circuit are the contacts of the trip relay. Other circuitry inside of the control panel controls the operation of this relay. An important point worth noting about this circuit includes the path followed by the B lead current of the generator. This source of power supplies two different inputs into the regulator. The first input point is to the operational amplifier. This is a constant path. The second route for power from the B lead is through the output control relay, into the control panel, back to the outside whirl through the contacts of the generator on relay, then back inside through the contacts of the trip relay. This is the source of power for most of the circuits within the control panel. So as you can easily see, if the generator output relay is open, or if the trip relay is open, or if the generator on relay is open, a circuit cannot be completed. Any of these three occurrences will disable the control panel and thus the generator as well. Functionally, these items are controlled as follows. The generator output relay is automatically controlled by the start circuit and is open from 0 to 60% during a ground start. This relay is not open during an air start. The trip relay is controlled internally by the control panel itself. As we will see in a few minutes, fault circuitry within the control panel will open this relay if any malfunctions are sensed. The generator on relay is controlled by the generator switch in the cockpit. This relay will only close when the generator switch is in the on position. The next major consideration in the generator circuit is regulation. Here is the internal components of the control panel involved in regulating the generator output. We'll start with the upper left corner with a component that resembles a transistor. This is an oscillator circuit which generates a constant stream of signal pulses. This output is fed to an operational amplifier that receives other inputs from the circuit as well. One of these inputs is power from the generator B lead through a potentiometer and then to the operational amplifier. The potentiometer is what is used to adjust the generator output voltage and is adjusted during the generator paralleling operation. The third input to the operational amplifier is provided by the paralleling circuit. We will discuss this circuit following the regulation function. Now let's consider the effect these three inputs have on the operational amplifier. The oscillator circuit sends a stream of constant pulses to the operational amplifier. If no other inputs were present, the output of the operational amplifier would be an identical stream of pulses, although the output strength would be stronger than the input. The other inputs connected to the operational amplifier will cause this input stream of pulses to vary. From the operational amplifier, the output travels to several transistors. These components serve only to amplify the output of the operational amplifier to a point that it can be supplied to the field of the generator, which we learn controls the generator's output. Note that before the signal reaches the generator, it must pass through the closed contacts of the reset portion of the trip relay and the generator output relay. The reset relay is internal in the control panel, and its tripping function is controlled by the fault circuitry within the control panel. The generator output relay has already been discussed and is controlled by the starting circuit. If either relay has opened, no signal will be provided to the A lead, and therefore the generator will have no output. Before we begin to discuss the regulation process in detail, let's add the paralleling circuitry so that the entire function can be covered at once. A paralleling operational amplifier is installed in each control panel. These amplifiers are connected to the D lead of their respective generator and to each other through pin K of the control panel. While the precise operation of these units is not important, suffice it to say that by using the inputs provided, each operational amplifier in each control panel will provide an output consistent with the load sharing status of its generator. If it senses that its generator is carrying more of the load, its output will be reduced. If it senses that its generator is carrying less of the load than the output of the other generator, its output will increase.
We're going to take a break to point out a very important principle of the generator system. Now, we've said already that the control panel is the brains of the system. And this is certainly true, but no brain could be any smarter than the input provided it. As our program continues, you'll find that many inputs are provided to the control panel simply to provide sensing information about the generator system. These connections are often overlooked in the troubleshooting operations. Here is a typical write-up. The pilot reported that the left-hand generator would not come on the line. When he moved the generator switch to the reset position, the voltage would climb to 31 volts and then drop back to 0. Have you got any idea what caused it? Well, first off, let's state that the voltage going back to 0 was correct. The overvoltage circuit in the control panel was sensing this level and properly shut things down. The problem was that the connection at pin D of the control panel was broken. This is the input source for generator voltage to be sensed by the control panel. Since the control panel didn't see anything there, it just kept turning up the output until the over-voltage circuit took over. The control panel was performing exactly as it should have, but because it did not have all the needed information, the result was a malfunctioning circuit. Keep those important sensing points in mind while troubleshooting the generator system.
Now let's consider some operational conditions and how they affect the regulation circuit. As soon as power is provided to the control panel, the oscillator circuit provides an output. This output is duplicated in the output of the operational amplifier and through the circuitry that boosts the signal level provided to the A-lead. Since we are now exciting the field, the output of the generator will begin to increase. Note that this increase in voltage produced is occurring without the main contactor being closed, nor the generator on the line. As the generator voltage increases, the voltage at the B lead will increase as well. This voltage makes its way to the operational amplifier, where it will at some point begin to counteract the signal provided by the oscillator circuit. The operational amplifier output will now decrease slightly, which will cause the A-lead current to decrease, which will in turn decrease the generator output. At some point, equilibrium will be reached and a regulated output is established. The generator output voltage and oscillator signal will be proportionately matched so that the operational amplifier will have a constant output. We can adjust the output voltage at which this equilibrium is reached through means of the potentiometer. If the generator voltage decreases, say because of a greater load being applied, more of the oscillator signal will act on the amplifier, which will cause its output to increase, and thereby increase the A-lead signal, which increases the output voltage of the generator. Because all of the components are solid state, these types of adjustments and reactions can take place instantly. Now we place the other generator on the line. The paralleling portion of the system now comes into play. This input will also have the effect of canceling out some of the oscillator output until a state of equilibrium in load sharing is reached. The result of this action will be exactly the same as before. If one generator begins to carry more of the load, the paralleling input to the opposite generator will cause the A-lead current for its generator to increase. As loads are applied to the bus and engine RPM changes, the regulator circuit in each control panel will vary its output to maintain generator output at the desired voltage setting and the sharing of the electrical load between the generators equal. The generator protection system consists of the previously discussed auto line contactor circuit and the feeder fault circuit. The auto line contactor circuit can open the main contactor relay, which will disconnect the generator from the aircraft bus system. The feeder fault circuit controls the tripping coil of the trip relay, which interrupts the field current being supplied to the A-lead of the generator. The feeder fault circuit is the same circuit as used in the battery fault system. Feeder fault transformers installed in the generator power and ground lines are connected to a diode bridge within the generator control panel. If a fault is sensed in this wiring, the SCR in the circuit will conduct and cause the trip relay to open, thereby disconnecting the field lead of the generator. The main contactor circuit can also open the trip relay via this other SCR if it senses an abnormality in the generator output, such as incorrect generator polarity or overvoltage. After the generator has been disconnected from the line because of a fault condition, or if the generator residual voltage is not sufficient to produce a generator output, it will be necessary to perform the reset function on the system. When the system is reset, the generator field will be supplied power to flash it, and several relays will be energized. The effects of each of these actions are as follows. When the generator switch is moved to the reset position, the reset relay energizes. The closed contacts of this relay will now provide bus power to the control panel and to a 400 ohm resistor connected to the A lead of the generator. Another set of contacts of this relay will complete a path for current to flow from the B lead of the generator to a pair of diodes within the control panel and to the A lead of the generator. Two relays within the control panel play an important part in the reset function. The trip relay will obviously be open at this time. Unlike most of the relays we have discussed up to this point, the trip relay is a two-coil relay that is not spring-loaded to either the trip or reset position. Electrical power must be used to open or trip the relay, and electrical power must be used to close or reset the relay. The second relay, which is referred to as the reset relay, is of conventional operation. It is spring-loaded to the normal position and energizes to move to the reset position when electrical power is supplied. The control panel reset relay, which is installed within the control panel itself, should not be confused with the system reset relay, which is installed in the airframe wiring. During normal operation, the control panel reset relay and the trip relay will both be closed. As you can see from this path, the reset relay is held closed by the output of the B lead of the generator. If the trip relay has opened, the current flow to the A lead will be interrupted, which means there will be no output from the B lead, and the reset relay will be open as well. We are now in a condition where the reset function must be used to bring the generator back online. When we move the generator switch to the reset position and the airframe installed reset relay closes, several events take place very quickly. The closed contacts of the system reset relay provide a path for B lead output to be connected directly to the field via the A lead. This immediately causes the generator output to begin rising. As this output flow increases, it will reach a point so that the control panel reset relay will energize. As it energizes, sufficient power will flow through the closed contacts of the relay to energize or reset the trip relay and move it to the closed position. The regulator circuit is now connected to the A lead and will begin controlling the generator output. However, if either the auto line contactor circuit or the generator feeder fault circuit sense abnormalities in the system, they will again open the trip relay and stop the generator's output.
Well, that covers the generator system. We hope you understand its operation better than you did before. This critical system has often been a needless problem in the field because of misunderstanding. Now, if you still feel uncertain about your knowledge of this system, consider re-watching these last two programs in about a week. Review the simplified schematics provided and carefully work out the circuit flow in your own mind. When troubleshooting, work carefully and methodically, and don't forget about those sensing circuits. Until our next program, good flying and good maintenance.